Okay. So, oh, how much battery do I have? Oh, plenty. Number 3 now. And that's the picture for number 3. So what you have in the picture is an airplane going around in a circle. So I'll just draw it again here. So you have the plane, and here's the center of the circle, and what they're saying is there's a weight of mg, and there's a lift force of L, and the angle here is theta. Now just be clear, that plane is going towards you. It's coming out of the board. So it's going around like this, okay? It's not this way. It's, we can see it's coming out and going around that point. Can you imagine that? It's coming out of the screen. Okay. So the force that's going in a circle must be going to here. How many forces are on this plane? There's 2 forces, right? 2 forces. And what I'm going to do is change this force into a vertical and a horizontal. So is this L cos theta or L sin theta? L cos theta. And this one here is L sin theta. This one here is the force that's making it go in a circle. So you have this here as the circle force. Sorry, I'm using bad English. The centripetal force. Okay? In the question, I tell you the radius, and I tell you the velocity, and the speed, yeah. And do I tell you the mass? I don't. Okay. I don't, do I? No. So which formula should you use for F? mv squared over r. So you know F equals mv squared over r. Yep. But you also know that F equals L sin theta. But you also know L cos theta equals mg. Now why is this? Why? Why is L cos theta equal mg? Yeah, you're right. It's not moving vertically, it's moving horizontally in a circle. So the up and the down must be equal, because it's not going up like this, it's just going around like this here. Okay. So what I'm going to do now is I'm going to say L equals mg over cos theta, and I'm going to put that in here. So now I get F equals mg sin theta over cos theta. Yeah. Yes, sine over cos is tan. Oh, sorry, got my mg. Mg tan theta. Now, this is equal to F, and this is equal to F, so we can put them together. mv squared over r equals mg tan theta. The m's cancel, so you get tan theta equals v squared over gr, which is the equation for banking in applied maths. Is that even? Oh, maybe they took that out of the new book. Banking. You don't know this word? It's the bicycle that leans at an angle when it goes around in a circle. No, they must have taken that out of the book. You have the blue book, not the brown book. Yeah, I guess. Yeah, if you look in the brown book, you'll see it there. It never comes up on the exam, so I guess that's why they took it out. Anyway, do you know the V?
Yes.
Yeah, and you know the G and you know the R. So if you take out your calculator, you have this number here?
Yeah.
Yeah, what is the number?
529 over...
Oh yeah, give it to me as a decimal, this number here. What is it?
0.8987.
Okay. So what does theta equal?
In radians, 0.73.
Yeah, so 0.73 radians, and what was it as degrees?
41.9, which makes it
41.9 degrees. Yeah, okay. Yeah. That's it, yeah. So it's not too bad, I hope, now that you've seen it. Yeah?
I just thought the things going around, like the rings going around.
Like this?
They're just going around, like on a stalk anyway. Like doing the barrels and yeah.
It's not complicated.
Yeah.
Okay, so can you finish those questions for me? Well, you really need to, because they're on, everything we're doing could be on the exam. Okay, so we'll go on to the next topic. Yes?
How much is in the break to...
Oh, yes, on your calculator. Shift, mode, radians, or degrees, you can pick. See that, Louis? Shift, mode, and then you can choose. There's radians now.
Yeah. In the question, it says say the body to shoulder degree and then
Well, I know I should have made it clearer. My advice is, if it doesn't say, you can use radians and you'll get full marks for sure.
Okay, so actually I need to pick the two for you.
No. I put the answers back in degrees, but I should have said this or this, degrees or radians. But in the exam, if you gave it to me for radians, that's fine, full marks, no problem. Okay. I said that the formulas need to be in radians. So then why did I give my answer in degrees? If you think about it, that angle theta, that's not the angle for the circle. It's a different angle. So I don't want to complicate or confuse things. I was just saying it was okay that I gave my answer in degrees. But if you want to be safe, just give it in radians. Okay. Yeah. Now, we have a couple of more topics to do this week. This topic really is in semester 2 on the syllabus, but I feel like I really must do this in semester 1. Because the topic after this, I don't know if anyone knows it, you would know it, simple harmonic motion. Do you know this word? No. Simple harmonic motion. Anyway, it's not important. What I'm saying is, this topic here is more of a semester 2 topic, but it's very, very easy, and it's better if I do it now than in semester 2. So what's Hooke's law talking about? Well, it deals with things like springs, anything that kind of stretches. So I'll just draw a spring as an example. So this is not moving, okay, it's not moving. Then what will happen? If I pull it, then the spring will have a force trying to stop me from pulling it. Which you know, when you pull a spring, it's difficult to pull it, right? Now, this distance here, people call it different names. You can call it x, or delta x, or ext, or you can call it e. And what it means is, in English, the word I'm thinking of is extension. Extension means like extra. So I usually call this distance delta x, and it's the distance you pull it. Okay. So in the first picture, delta x is 0. You're not pulling it. And in the second picture, maybe delta x is 5 centimeters or whatever. Okay. So you understand what I mean when I say delta x? Yeah. So for example,
The force turned back.
well, it's just for the moment, it's just the distance you call it. Yeah, just the distance for the moment. I don't have anything stretchy. Right? Anyone got an elastic band or something? Stretchy? Yeah. So like here, the delta x is 0, and then if I pull it 1 centimeter, then the delta x is 1 centimeter, and then 2 centimeters and 3 centimeters. But if I let go, you see it goes back because there's a force. There's a force that wants to bring it back to its natural length. How can you calculate this force? Well, that's Hooke's law. Hooke says, yeah, ultimately, but just before that, Hooke says F is proportional to delta x. Now, I don't know, do you do this symbol in chemistry? Have you seen this before?
Delta.
No, the proportional. No? So you don't know what this symbol means? Yeah, so what it means, what you're saying here is, if you make this twice as big, then the force here is twice as big. And if you make it 3 times bigger, then it's 3 times bigger. Now, yes, go on, Louise. No, that's what I was just about to say. It doesn't mean the same. It means, if I give you an example here, I'll give you an example here. Let me think about this room. Yeah, okay. A simple example might be, you all pay fees for the course. Yeah. So if there's twice as many students in this room, then there is twice as many fees paid, correct? And if there are 3 times as many students, then there will be 3 times as many fees. But notice, I'm not saying if there are twice as many students, then there are 2 fees. They're not equal. I'm saying they're the same relationship, that if I make the students twice as many, then the fees will also be twice as many, that they move together. Okay? So if I have 1 centimeter, but then it increases to 2 centimeters, that's twice as big, so the force now is also twice as big. And if I have 3 centimeters, then it's 3 times bigger than the 1 centimeter force. Okay? Now you might say, so it's not useful because I can't tell you what the force is. I can only tell you, oh, it's twice as big or it's 3 times as big. So the formula which you were saying, Ugo, a second ago, which is what you really care about, is that F equals K delta X. And this here is called, well, it has many names. We can call it the spring constant. We can call it the stiffness constant. I suppose you could call it Hooke's constant. But it's just a constant. And it's very important that you know that the K is different for different springs. So it's different for each problem. Now, I'm going to put a minus here. Yeah, just to make it really, really clear that if I pull to the right, the force is to the left. Okay, so the minus there is to remind me to the right, the force goes to the left. Okay, so I mean, let's have a look at some simple examples just to get started with this. So this is called Hooke's law. Okay. Can I go down? Yep. So, and it doesn't have to be a spring. It could be a string, a rubber band, Hugo's coat. It's just anything that stretches. Okay. A string has natural length of 2 meters and elastic constant, that's another name for the constant, elastic constant or spring constant, or there's so many names for it. Elastic constant of, oh yeah, I forgot to say, what's the unit for K? What's the unit for K? Look at it, what's the unit for K? Oh, does indeed. Yep.
The constant.
No, it does not. K has a unit for sure. Come on, you know it. What's the unit for K? What's the formula? Yes, yes? Newtons per meter. Yes, yes. Do you see why? Look, yeah, if I just bring the delta x to the left, I get K equals F over delta x. So what's the units for x? Newtons. And x? Meters. Do you see that or not? No? Let me show you. So if you look here, F equals K delta x. F over delta x equals K. What's the Louise, what's the units for F here? What do we measure force in? Newtons. And what do we measure distance in? Meters, yeah. So the K is newtons per meter. Yeah, that's okay? You got it? Okay. So, has this elastic constant of 10 newtons per meter. Find the force if the extension, well, no, actually, no, I know this. Find the force if the length is, so I'll do 3. 1, 2, 3. 3 meters, 4 meters, 5 meters. Okay. When you're ready, I'll do it. Did you write it down? Yeah. So, first one here, let's write the answer beside it. What's the formula for F? It is K delta X. What's the K? 10. And what's the delta X?
1.
Oh, good. I thought I was going to trick you. Tell us why it's 1 and not 3. Yeah, the natural is 2 and the length is 3, so the extension is 1. Can you see that? So, look, I said the natural length is 2. So if I move this to 3, the extension is 1 meter. I was hoping I'd trick you, but I didn't. It's hard to trick you, yeah. I one day I will. So the answer is 10. Okay. F equals K delta X. So here this is 10 multiply, what number here? 2, so it's 20 newtons. And then here, F equals K delta X, so that one is 10 multiply, what's the number here? 3, yeah. Which is 30 newtons. So you can see, the more you stretch, the more force is trying to stop you. Yep. Okay. Okay, I'll do another one now. So that's kind of a simple one to get started with for Hooke's law. Do you have that taken down? Yeah. Okay, so now a more difficult one. Okay. So there's 2 strings. There's 2 strings, a ball between the strings and the 2 walls here. And the distance from here to here, let's just say it is 5 meters. And the natural length, sorry, you know what I mean when I say natural length, don't you? I mean the length when it's just not doing anything, it's rest length. Yeah. So, actually let's make this an even number, let's say 6 meters. So the natural length here is 1 meter, and the natural length here is 1 meter. And the constant here, let's say it is, I don't know, 10 newtons per meter. And the constant here is, let's say it is 20 newtons per meter. Yeah? Now in this picture, the ball will not stay at rest. The ball will start to move. So, well, I don't say anything yet. Just think for a moment. I want you to think about it. Will this ball move to the left or will it move to the right? Have a think. I'll give you a few seconds to think, and then I'll see what you think. Okay. So, is it going left or is it going right? Right. And the reason? The force is bigger because remember, force equals K delta X, and it's a bigger K. So the force is bigger to the right. So the ball will move to the right. Okay. So my question is, how much force is on the ball? So how many forces are on the ball? There are 2 forces, one to the right and one to the left. So the force to the right. So what I'll do is I'll get Ibrahim and then maybe Louise that give me these ones. So Ibrahim, the force to the right. What's the formula? K delta X. So what K do I use here? 20. And what's the delta X? Ah, gotcha! Not one. What is it? Anyone else? 2. Now tell us why it's 2.
It's 6. Not sure that it's 3 minutes, 1 minute, 2.
Yeah. So you look, how far apart are the walls? 6. And if it's in the middle, that's 3. 3 meters, yeah, so it's 6. If you look here, yeah, so it's 3. Okay. Now, what's the natural length of the string? 1. So if it is 3 and it was 1, then what's the extension? 2. You see why it's 2? Yes. Because it was 1 and it's now 3, so its extension is 2. Okay, so that should be a 2 there. Okay, so Louise, can you then tell me now for the one to the left? What do I have here? So it's going to be like this one.
Yeah.
It's K, what's the formula? K delta X, yeah. 10, yeah.
Times.
Yeah, 2. Yeah. So this here is 20. So if you look at the ball, there are 40 newtons this way, and then there are 20 newtons this way. So in total, how many newtons to the right? 20 newtons in total to the right. I can't, how long have you lived in Ireland, Hugo?
I have a clue.
Oh, right, okay. So it's going to move to the right with a force of 20 newtons. Okay. Now my next part of the question is, where must I put the ball so it doesn't move? Do you understand? So I want to know, where do I put the ball so it's balanced, doesn't move? It's got to be somewhere to the right, isn't it? Maybe 2 meters? Maybe not. So we have to calculate it. So it's the same problem. Can I go down? Yeah. So we don't know, but we think it should be somewhere to the right because that's where it wants to move to. Now, if this distance here is, I'll call this one X. Hold on. 1 second. If I call this one here, which do I want to call X? I'll call this one X. This one X. No, it doesn't matter. If I call this one X, then this one here must be 6 minus X. Because the total is 6. So for example, if this is 1, then the other piece is 5. This is 2, then the other piece is 4. And if it's 3, the other piece is 3, and so on. So if it's X, the other piece is 6 minus X. 2? Alright, okay. Well, we'll get to it. Okay.
Down to here, it's actually 4.
In this one here, okay. It would be, because they're in proportion, so yeah, it should be 4. Okay. Now, Hugo, your turn. Force to the left, what's that here? So give me the formula and then give me the numbers. So the formula is K delta X. Now the K is what? 10. No, not X. Nope. I didn't trick 2, but I managed to get Hugo and Abraham, so I'll settle for that. Not X and not 6 minus X.
6 and 1?
Yes, X minus 1. Yep. Now I know why you're thinking it's X, but it's X minus 1 because we're still talking about extension. And the natural length is still 1. And if its current length is X, it should be X minus 1. Do you see why it's X minus 1? No, you can't. What's the natural length? 1. No, the natural length is 1. So if its length is 3, what's the extension? 2. If this length is x, what's the extension? Yeah, x minus 1. Okay. Who? Give me the one to the right. I know I won't trick you though. What is it? K delta x, yeah.
20
Yeah.
and 6 minus x minus 1.
Yeah. Not bad. Can you see why I got this one? Because what's the length? The length is 6 minus x. And what's the natural length? Is 1. So the extension is 6 minus x minus 1 is the extension. I know there's lots of words I'm using. Can you see why it's this or not? Not very clear. I suppose you can just think about it like this. So like Louise, it is 5 meters long, but the natural length is 1 meter, then what's the extension? 4, yeah, because in your head you did 5 minus 1. If the length is x, then the extension is x minus 1. If the length is 6 minus x, the extension is 6 minus x minus 1. It's still the same idea. Okay. Yep. So we now have 10 x minus 1 equals 20, and together this is 5 minus x. Now, what I'm doing is I'm saying the force to the left equals the force to the right, because I want it balanced. I want it balanced. So you get x minus 1 equals 2, 5 minus x. So I get x minus 1 equals 10 minus 2x. So I get 3x equals 11. Ah, so it's not 4, is it? Yeah, no.
It's 3.667.
X equals 11 over 3, which is
3.667. So 6 continues it.
yeah, so not quite 4. So if you put it at 3.67 meters from the wall, the two will balance. Okay. You could get this in the exam, although the next example I'm going to do is the one which they like for the exam. They really like in the exam the questions, which you would have seen before, hanging something from the ceiling. So like you have a spring, and you put a weight on it, and then it goes down. Okay. This is the type that they like. So I'll do one of those now. Can I scroll down? Yep. Okay, so what I have a spring, and its natural length, I'll say it's 0.5 meters, and its constant, let's say it is, I don't know, 64 newtons per meter. Okay, so what I'm going to do is I'm going to take this, put it on the ceiling, and then I'm going to put a 2 kilogram mass here. And what will happen is it will stretch down. And my question is, what will be the length of the spring after you put the mass on it of 2 kilograms? So do you understand what is happening in this question? Yes or no? No is okay. You understand what I'm saying here?
Find the length.
Find the length. Yeah. So what I do is I take the mass, I put it on the spring, and then it goes, oh, and I want to know the length. So at the beginning, what's the length? 0.5. And then I put the mass on it, and then what happens? It increases. I would like to find the length. So, can I go down? You have this picture? Okay. So what's going to happen is, it's going to go like this. Extend down. Now, how many forces are on this mass? How many forces? Yeah, what are they?
Gravity.
Gravity, yes, so as you said, Abraham, mg. And Hooke's law, which is K delta x. Is this moving at the end? No, it falls down and then it's balanced. So, that means we can say mg equals K delta x. So then mg over K equals delta x. Do we know m? Yes. Do we know g? Yes. Do we know K? Yes. So I get delta x equals 2 times 9.81 over 64. So can you tell me what that is, please? So 0.7. 0.307. Is that the answer?
No.
No? What do I have to do now? I have to add it to the 0.5 because this is only the extension. What I worked out was this is 0.307. So I still need to add onto it the original 0.5. So then the final answer, the length is 0.807 meters, or roughly 81 centimeters. Let's see, do I want anything? Now, in the exam, it'd be a little bit more common to go backwards. The exam question would say, if the length is 81 centimeters, what was the K? The constant, yeah. So I think what I'll do is, I'll give you one to try, and then I'll do it on the board in a minute. And then I'll give you, let you try the question. So can I scroll down? Yeah. So what you have here, so this would be more like what you get in the exam. You have a spring. Let's say its length is 0.75 meters. And then you come along and you put a mass at the end. And this is a 1 kilogram mass. And because you did that, the length is now 1 meter instead of 0.75. Okay? So what I want everybody to do for me now is calculate the K. I want the K here. You got anything from it? let's see if we all get the same one. So what's your... Okay. Let's see, we already have differences. And what else did you get? Okay, some similarity, so... I think you made a mistake, maybe. Did you get an answer, Louisa? Not yet, okay. So you're right, yes, you got the right formula. Good, okay. I'll just give you another minute or two more minutes, and then I'll do it. Did you get an answer, Young? What did you get for K? Let's see, 39.24. Good job. That's the same as you, isn't it? Yeah. Okay, who am I waiting for? Abraham, you're recalculating? Oh dear, it's not working for you today. No. And then you are calculating. Okay. Yeah, let's see. Keep going. Don't worry. Keep going. Yeah, so you have mg, yeah, k delta x. So do you know the m is 1? Do you know the g? Yeah. Do you know the k? No. Do you know the delta x? You do. What's the delta x? What's the extension? Yeah, tell me what number? Yeah, what number for this? Here. Not 7.5, no? Yeah, 0.25.
So 1 minus 0.
So
Yeah.
actually, I need to...
You do it.
Yes.
I'm going
No, I'm not sure what you're doing here. Let me have a look. This is your formula. This is correct. So the m of the m, 1. What's the g? 9.81. Equals, what's the k? You don't know. Just k. And what's the delta x? 0.25. Now can you see why? Why is 0.25? Yeah, because first it's this, and then it's this. The extension is the difference. It's the extra piece. So tell me what the k is from here. Did you get it? Alright, so I don't think I'll do it on the board since it looks like you all got it. Correct, okay, so since you all got it, I won't do it on the board. The K, I'll just write the answer down, so if you watch the video later you can check if you got it right. K equals, what was it, 30?
9.24.
Yeah, now don't be lazy, give me the units as well. Newtons per meter. And 2.4, 2.5? 2.4, so, okay. Alright. Now, I won't do another example, but this is where things start getting more complicated in physics, because you can now do things like, you could put this together with what we did earlier today. So for example, here, you have your spring, and now you turn this around in a circle. Okay? So you have this formula from Newton, this formula for, we'll go with m omega squared or, but you also have this formula, mv squared over or, but because it's a spring, you also have F equals K delta X. So I'm just saying it's very, very common in the physics subject and exam to mix different types of problems. So we could have, for example, a spring and a circle problem together. So you have your spring going around in a circle. Do you understand what I'm saying here? How does that make it different Well, it just means you have more formulas you can use, really. That's all that really matters at the end. I'm trying to think. Can we think of anything else that we did that mixes different topics together? Not so much. Yeah, not really so much. You see, what will happen is, as we cover more and more of the course, we can mix more different things together, you know. So I'm just saying, when things get mixed together, like in my example of the spring and going in a circle, it just means you have more formulas you can use. That's all, really. Okay.
Would the R be different then? Or would it still
It would still be the radius of the circular motion.
So would it still extend it, like if it's being spun around?
The R would not be the natural length. Oh, the tensions would be changing. Well, this is the thing. If I'm doing it like this, the tensions would be changing. It's going around like this. But if it was going around like this, it stays flat. Yeah. That might, I think this one would be too difficult for the example. Maybe horizontally would be okay. Anyway, that is a more difficult one. Let me have a look. Yeah, I think you can try. Yes, definitely try. Okay, so for a few minutes, I want you to try some of the questions on the next page on Hooke's law, 1 to 9. Yeah, try your best, 1 to 9.